Welcome everyone. We have a speaker from GeoSoftware today, Kirill, and Pasha is also with us from GeoSoftware. I'll first invite Pasha to showcase some uh, promotional material, and then I'll introduce Kirill. Then we can start with our presentation.
Okay, hello everybody. My name is Pasha. I am a business manager for GeoSoftware based in London. My colleague Kirill is based in Netherlands. So we have a couple of offices here in Europe and also office in Egypt. I'm part of EMEA team, Europe, Africa and Middle East. Now, it's going to be a very short introduction. Not even sure whether I'm going through all the formalities in terms of, showing you the corporate updates, etc., because hackathon is more like informal events anyway. So just wanted to say a few words about GeoSoftware. Some of you probably aware of this company. Some of you haven't heard of this, but maybe heard previously. So there's been some changes over the years. But in a nutshell, we are really dealing here, and Kirill is going to show some cases today based in Hampson Russell software. Hampson Russell has been founded in mid-80s in Canada. It's a Canadian company. And over the years, we've made some acquisitions. There were some mergers, long history. So we got a number of customers in Europe. Pretty much everybody use our software one way or another. So in terms of easy to use Windows-based inversion, we're pretty much like industry standard in the States, in Canada, in Europe, and also in parts of Asia, notably in Asia Pacific. We also, as a part of our portfolio, have software called JSON, Geoscience Workbench. Maybe some of you heard about this. It's a Dutch company, or used to be a Dutch company. And it's also inversion product, but it's Linux-based, Windows-based. It's a heavyweight, specialized inversion product. We're not really going to focus on this today. And the third one that we're dealing with is called PowerLog for petrophysical interpretation and analysis. Now, these are three sort of packages we're generally dealing with. Now, as a GeoSoftware, we used to be a part of the company called CGG. Canad has got the logo on the background. CGG, it was a spin-off from CGG. We are not really related anymore, although CGG is our big customer. And thank you, Canad, for this as a representative of CGG here. So we're dealing very close with each other, still friends, but we are a separate company now, and we have an investment vehicle in Canada. And part of this investment company, the bigger company, there are also two others. First called GeoActive. For those of you who are not aware, this is IP, Interactive Petrophysics, and another one called Petrosys. This is for mapping, Windows-based mapping applications. But we are not really talking about these two. So today, it is mostly Hampson Russell inversion. Kirill is a part of the Geoscience Services team based in Netherlands. And as again, for those of you who's joined, I'm based in the UK. So in the longer term, after this hackathon, if you're interested in anything in particular, you can reach out to Kirill, of course. You can reach out to organizers, and I'm sure they will pass some information over to us. And we can provide you more information, some extra presentations, extra materials. You always can go to geosoftware.com website. Now, also, the website is going to be changed. Now, we got very ambitious R&D roadmap, and it's heavily focused on machine learning, on convolutional neural networks to apply on pre-stack data, which is fairly unique. And the fairly unique bit about our software in Hampson Russell is that this convolutional neural networks that we use, you also can use, as a background, use the elastic properties for this and rock modeling. So it's still very geoscience oriented. It's not really purely data science, machine learning up in the air, applied on the big data, but also with some geoscience, geophysical, geological background for it. And we're quite uniquely positioned in this field. And currently we're working on GAN networks as well. Anyway, I think now it's almost 5 minutes I used my slot. And I pass it over to Kanad and to Kirill. And yeah, thank you very much for participating, and we'll look forward to deal with you here.
Thanks a lot, Pasha, for that quick introduction. I'll now introduce Kirill, and I'll share his bio with all of you. So Kirill is part of the GeoSoftware company, which is our sister company, as Pasha previously mentioned, although separately. But yeah, he works as a geophysicist in GeoSoftware with an excellent and solid background in the history of working in various regions, locations, and an excellent technical background. He's presently looking after technical support as part of the organization, and he has master's degree in exploration geophysics. And yeah, I welcome him to share his presentation with all of us. And can I just ask everyone if you have any questions during this presentation, please can you type it in the chat box, and subsequently then upon completion of presentation, he will be happy to take some questions from the questions that might have come up. Yeah. With that done, I would like to invite Kirill to start his presentation. Kirill, can you please share your screen?
Yeah, sure. So firstly, thank you, Kanad and Pasha, for a great introduction of GeoSoftware, of me. So let me just stop my video and share my screen. So now you should see my screen. Please confirm. Are you?
Yes, we can see that. Go ahead.
Thank you. Yeah. So again, thanks for this opportunity to give this talk today. I appreciate all of you for joining me today. And my topic is seismic inversion and rock physics-based reservoir characterization. And basically, what I want to discuss is the use of GeoSoftware applications for geothermal energy projects. So here you can see, let's say, outline of my presentation. So I will begin with a very brief introduction, and then we will explore two different case studies. So I have prepared these two case studies, each demonstrating different approach or different workflow, what GeoSoftware can offer for geothermal projects. The first case study, focusing on Cambrian Deadwood Sandstone Reservoir in Canada, presents a workflow which involves seismic inversion, followed by machine learning. So with seismic data available, we perform seismic inversion to obtain elastic properties. However, for geothermal studies, for geothermal projects, two most critical properties are porosity and permeability. Therefore, we will discuss how, when we, in the next step, we derive these crucial parameters of porosity and permeability from these elastic properties, and how machine learning plays an important role in this process. And the second case study, focusing on the Dagger Formation Carbonate Reservoir from France, it illustrates a workflow based on rock physics-driven machine learning. So in situations where, for example, only a few wells are available, perhaps only a single well, obtaining reliable solutions using seismic inversion might become challenging. In such cases, we can explore another workflow. We can generate many pseudo wells based on rock physics modeling. Then we can generate corresponding synthetic seismic gathers for each of those pseudo wells and use this synthetic dataset to train a neural network on that. Subsequently, after the training, we can apply this trained neural network operator to our actual seismic gatherers and obtain direct results in form of target properties such as porosity. So any log property can be used as a target. And this workflow is showcased in this second case study. So during my presentation today, I will delve into these two workflows, and let's start with some kind of introduction slides. So basically, since 1980s, we have been used 3D seismic data, 3D seismic techniques successfully in the search for hydrocarbons, which is driven by measured advances in seismic acquisition and processing technology. And if you look at that figure on the right, you can see there is geothermal energy and CO2 monitoring aware. Which are considered as a green technology, and they are a part of this broader spectrum of unconventional uses for geophysics. And the question is, as we transform to this green energy, are there any applications of 3D seismic that can help us in this transformation? And the answer is yes. Well and seismic data can be used together as the basis for both approaches. So in this talk, I will illustrate, as I said, GeoSoftware techniques, the software technologies, which can be applied to geothermal projects. So basically, as Pasha mentioned in his introduction, our portfolio consists of 3 different softwares: PowerLog, Hampson-Russell, and JSON. So PowerLog is a comprehensive suite for petrophysical analysis and petrophysical interpretation. So high quality well data is essential for both for inversion and machine learning approaches. And each project is started with its well data QC and well data conditioning. And also we have Hampson-Russell and JSON, which are really well-known software for reservoir characterization, and GeoSoftware provides a range of software tools inside with Hampson-Russell and JSON that allows our users to analyze suitable locations for geothermal projects. These technologies including rock physics analysis, basic seismic analysis and display, seismic attribute analysis, AVO analysis modeling and pre-stack inversion, seismic phases analysis, time-lapse analysis, multi-component analysis, azimuthal and fracture analysis, and machine learning prediction of reservoir parameters. Additionally, Python ecosystem is available in our software, which is a direct link to any Python applications. So I will recommend you to join a talk by my colleague Pavel Didenko next week, next Thursday, I believe. So he will cover this Python ecosystem topic, particularly how we can use it and what kind of benefits we can obtain. So don't miss this opportunity to join him next Thursday. Let's now start with case studies, and we start now consider first case study, which is Cambrian Deadwood Sandstone Reservoir, Canada. So this is a geothermal project, and with DEEP, Deep Earth Energy Production Corporation, has targeted the basal sandstones of the Williston Basin for geothermal production. The project is located just north of a border with North Dakota, so it's a boundary between Canada and United States. And the Cambrian Deadwood Sandstone Reservoir will be exploited by an array of horizontal producer and injector wells. And seismic inversion and machine learning techniques will be used to analyze Deadwood Sand Reservoir over 231 square kilometers of 3D seismic data. So, seismic inversion and machine learning. Let's now consider these two topics. And I start with seismic inversion. Just a few words about definition. So inversion, seismic inversion, is the process of extracting from the seismic data, shown here on the left, the underlying geology, which gave rise to that seismic. Seismic amplitudes, which are again on the left, shows us the boundaries between different rock layers. And during inversion, after inversion, we derive impedance, we derive elastic properties from seismic data. For example, P impedance shown here, it's on the right, which is not boundaries, which shows not boundaries, but it shows interval property, which are useful for subsequent geological interpretation. Why perform seismic inversion at all? So firstly, it gives us ability to incorporate well log information into seismic volumes. So we can integrate these two different types of measurements, I mean well logs and seismic data, and reduce the uncertainty and get more accurate results of reservoir model building. Next is we can increase the bandwidth and therefore resolution. So yes, some of seismic inversion methods allows us to increase the resolution. As I already said, inversion allows us to obtain interval Rafevan boundary values. We can remove varied effects. Inversion helps us to understand phase effects and optionally correct for them, identify lithology, pore fill, and porosity changes due to P wave and or density changes. And of course, we have when we have inversion results, it gives us ability for easier, more accurate interpretation of our sections. So now we know why we need to perform seismic inversion, in which cases it could be helpful. And let's now just quickly review seismic inversion approaches. So globally, there are many different seismic inversion algorithms, and globally they can be separated into two big groups. Deterministic methods and stochastic methods. The main difference between these two different groups, between these two different approaches is in case of deterministic inversion, we have a result in the form of single model of elastic property. So in case of stochastic inversion, we have multiple equally probable models of elastic properties. For example, 100 models of P impedance, which are, as I mentioned, equally probable. And this fact gives us ability to estimate uncertainty of a final result. There are also some other differences, of course, between deterministic and stochastic inversions. I will review them later during my today's presentation. So globally, all seismic inversion methods can be separated into these two big groups, deterministic and stochastic inversions methods, and each of these methods could be run as acoustic and as a simultaneous inversion. The difference here is in case of acoustic inversion, we invert only for P impedance. So if we can separate, if we do feasibility study before inversion, if we can separate reservoir facies, reservoir zones based on only P impedance, we can use acoustic inversion approach. If for this separation we need to include more than one elastic property, more than P impedance. So if the usage of P impedance is insufficient to see the separation, we need to run with simultaneous inversion. So simultaneous inversion means that we invert for several elastic properties at a time, for example, for P impedance, S impedance, and density. So these are seismic inversion approaches, and let's now delve deeply into them. And I start with deterministic inversion. Let's start with it. Sorry, here should be animation. So basically, there are many different deterministic inversion algorithms, and you can find different algorithms in different software. Here on this slide, I just put deterministic inversion algorithms which are realized in our software in Hampson-Russell in JSON. So each of the algorithms, of course, has its own advantages and disadvantages, and we can use them based on the challenge. We can select which algorithm we use based on the challenge, based on the time, based on the basically mostly based on geological challenge we have. I will not consider each of them in details right now. So for that we have a training course, really great training course where we can do it if you are interested. So now I want to discuss one of maybe most commonly used deterministic inversion workflow, which is model-based inversion. And this inversion method was used in the case study I will show you later. So we have a set of input data. At the beginning of our project, we have input seismic data and well log data. As I already mentioned, high quality of those type of data is essential, of course. Therefore, input data must be conditioned, both seismic data and well data. And also we have interpretation. Here I mean peaked horizons and fault surfaces, if they are. So having all this data, we perform firstly well-to seismic tie and perform wavelet estimation. After this step, we have wavelet or wavelets if we need to take into account wavelet change from the geology. We have, after this process, we have wavelets, which we are going to use for seismic inversion, and we have these final tied wells. Then, based on interpretation, based on this interpretation and based on these final tight wells, we create initial models, or also we call them low frequency models or initial models by interpolating of these well curves using our interpretation. So if we run deterministic acoustic inversion, we only need a model of P impedance. And if we run simultaneous inversion, we need low frequency models of P impedance, S impedance, and density. So okay, we created these low frequency models, and in case of this model-based inversion workflow, this low frequency model is our starting solution. So the algorithm uses this low frequency model as a starting solution and compares with synthetic trace we have after inversion, which is shown here in red. Algorithm compares with synthetic trace, which we have after inversion, and real seismic trace. And the model using which we have the best match together with the smallest error at well location is our final solution. So finally, we have a result in the form of volumes of elastic parameters. Again, in case of acoustic inversion, it is P impedance only. In case of simultaneous inversion, it's models of P impedance, S impedance, and density, and also any, let's say, derivative like VPVS is shown here, basically on the parameterization we use. So as I mentioned before, of course, each inversion method has its own advantages and limitations or pros and cons, and the benefits of deterministic inversion are basically consistent with the reasons why we should perform seismic inversion at all. I was thinking about, I was talking about them several slides before. I mean about these benefits. And as for limitations of deterministic inversion, they are, firstly, the resolution is limited by the resolution of seismic data is limited by the frequency range that we have in this seismic data. So as we know, it is limited. There is no low and high frequency. There is no information about low and high frequencies, and this fact doesn't allow us to solve, for example, for 18 reservoirs. And secondly, for all deterministic methods, only one single solution can be obtained, and therefore there is no possibility to estimate a probability and perform uncertainty analysis. So as a result, solving actual geological problems is not always possible using deterministic inversion methods. For example, if we are dealing with this thin layer geology. And the solution for this challenge may be stochastic inversion. So let's move on to consider it. If we consider resolution of deterministic and stochastics, we see the following. Firstly, seismic data lacks information about, as I already said, about low frequencies. And in order to obtain final result in absolute rather than relative values of elastic properties, in both cases, I mean both for deterministic and for stochastic inversion, low frequency model is used to fill this gap in low frequency information. So result in low frequency range is controlled by a low frequency model, and it's very important to build it accurate. The result in the area of, let's say, medium frequency range, shown here using this blue color, again, both in the case of deterministic inversion and in the case of stochastic inversion, is controlled directly by seismic data. What's the difference between deterministic and stochastics? And the difference is in the high frequency range, shown here using this green color. So recovery of high frequencies occurs only in case of using of stochastic inversion. It happens due to variogram modeling and statistical analysis. So I will give you more details a little bit later. So in case of stochastic inversion, due to this fact that high frequencies are recovered, we have opportunity to obtain more detailed result and highlight much thinner layers. But stochastic inversion requires much larger amount of input data to generate statistics. And also stochastic inversion is usually performed in a small window, in some small window, in order to exclude the influence of above and underlying layers, to exclude this influence on the overall statistical picture, let's say. Now let's consider different geological model building approaches. So if we consider them, we will see the following. Basically, there are three most commonly used approaches. First is, let's say, classic geological modeling. Using it, we obtain high vertical detailization. We are able to perform probability analysis, but our final model is valid only in the area of surrounding the wells, and there is a very weak integration with seismic data. Second approach is deterministic inversion. Using it, we can obtain high lateral detailization. We can perform independent assessment of reservoir properties from seismic data, but vertical detailization is low in this case, and we have only one solution and cannot assess the uncertainty. And finally, the third approach is stochastic inversion. And using stochastic inversion, we basically don't have any but, which I mentioned below. So we have high lateral and vertical detailization. We can evaluate reservoir properties from seismic data. Our model is aligned with drilling data, and we have probability analysis capabilities. Let's now talk about stochastic inversion workflow. So we use many initial information for that, or how we also call them. It's our hypothesis. So this is our knowledge about geology of a region and of an object, target reservoir, obtained rock physics relationships, ideas about degree of changes in properties described using these variograms, generated stratigraphic geological grid, description of distribution of elastic properties using these PDF probability density functions, data about fluid contacts, facies proportions, and expected signal to noise ratio in seismic data. On the other hand, we have a large number of field data, or how we call them, observations, with seismic data and wavelets, which we extract from this seismic data, and well data, of course. All this information is combined using probability density functions and the Bayesian concept. Next, sequential Gaussian simulation or Markov chain Monte Carlo algorithms is used. So it depends, the choice of algorithms depends on the software you use. So in Hampson Russell, we have sequential Gaussian simulation. In JSON, we have Markov chain Monte Carlo algorithms. And we use these algorithms to obtain a final results in the form of reservoir models. And the detail of these models is unattainable when using deterministic algorithms. So to summarize all things, what I said previously, stochastic inversion has several advantages over deterministic inversion and classical geomodeling in estimating reservoir properties. The first is high vertical details, which is achieved by using vertical variograms parameterized using well data, using well logs. The second is high lateral details, achieved by using seismic data itself, and additionally by using of horizontal variograms. And the third is ability to estimate prediction accuracy, which is a product of analysis of a large number of computed realizations. And here, just one simple picture, just simple example. Here we can see the difference between deterministic and stochastic inversion results. So deterministic inversion results, which is shown on the left, requires as you see, requires downscaling for integration in the fine-scale geomodel. And the results after stochastic inversion can be integrated directly. So it's very detailed. It can be integrated directly in this geomodel grid without any rescaling. I've after deterministic or after geostatistical stochastic inversion, geostatistical inversion, we have result in form of elastic properties. In case of deterministics, we have a single model for each of these properties, or only P impedance if we perform acoustic inversion, as you remember. So in case of geostatistical inversion, we have multiple realizations of each of these elastic parameters. And there is also ability to calculate multiple realizations of Lithophages models in case of geostatistical inversion. And the question here is how to obtain porosity and permeability estimates, which are really essential for geothermal projects, for geothermal studies. So let's now consider how porosity and permeability volumes might be predicted when we have inversion results in the form of elastic volumes properties after inversion. Typically, most common methods for porosity prediction based on inversion results are based on rock physics modeling, when based on P impedance versus porosity relationship. It might be even linear regression. Then is multilinear regression, co-simulation, and last is machine learning. And for permeability prediction, it's again might be done based on rock physics modeling and also based on porosity versus permeability relationship. This approach was used in this case study I will show you a little bit later. And also it could be done based on laboratory measurements on core data. So all these facts, what I mentioned here, leads us to machine learning, as typically using machine learning, it allows us to get more accurate results than using, for example, conventional regression approach for porosity prediction based on inversion results. So all these facts leads us to machine learning, and let's now consider this machine learning. Again, I'm not going to delve deeply into the details, into the theory of machine learning in this presentation today. If you want to know more about this, please join my colleague Pavel Didenko next Thursday, and he will cover this topic in his presentation as well. Today, I just want to highlight deep neural network what we have in Hampson-Russell. And as I said at the very beginning of this presentation, Hampson-Russell has really great machine learning capabilities. So, as you know, as you might notice, machine learning or neural networks becomes more and more popular every day. And deep neural networks are considered as the most advanced neural networks. Basically, there are two ways to run deep neural networks in Hampson-Russell with emerge DFNN, which is just a name of model. Emerge in Hampson-Russell, emerge DFNN, deep feed-forward neural network, and GOI CNN. Again, GOI is a name of model, and CNN is convolutional neural network. So if we're talking about emerge, is a deep feed-forward neural network. It's not something new in Hampson-Russell. We have it for many years, and it really gives us fine results. Emerge works on post-stack seismic data, and users must generate and select a series of post-stack attributes to be used as input data here. And using this emerge, we can estimate only one target property at a time. And this is not same in GOI CNN, convolutional neural network. Here, the inputs are seismic gathers directly, and the attributes are automatically generated and selected by the algorithm, by CNN. Also, due to the nature of this algorithm, multiple targets can be estimated simultaneously. And now, at this part of my talk, of my today's talk, I will discuss this left part, emerge DFNN, where the inputs is a series of attributes, as you remember. And using these input attributes, we can predict any target property, for example, porosity, what we're looking for. How it works: Emerge is a program that analyzes well log and seismic attributes at well locations. Then it finds relationship between log and seismic attributes at well locations, and it uses this relationship to predict or to estimate a volume of log property at all the other locations of the seismic volume. So after seismic inversion, as you remember, we have volumes of elastic properties, P impedance, S impedance, and so on. And we can use these volume attributes as input attributes for neural network in order to predict porosity volume, which we need for now for this geothermal study. So let's back to this case study. We already discussed this slide with general information about project, about location. Just a few words about reservoir geology. So the temperature of Deadwood Reservoir is somewhere greater than 120 degrees by Celsius. And the Deadwood Reservoir basically target sandstone is the 20 to 25 meter thick. As I already said, a reservoir will be exploited by an array of horizontal producer and injector wells. Here you can see a scheme of this array. And our objective for this study is to map porosity and permeability in this target zone using pre-stack inversion and machine learning. So a few words about input data. It was 3D seismic data, and with three wells were used. Input seismic data was a set of 3D post-stack time-migrated gathers, and these wells 1 and well 2 are vertical, and well 3 was deviated. And since there are no wells in this, let's say, west area, I will show results only east of this dashed line. This figure shows the well logs from one of the wells from well 1 over the geothermal target. So we have, they had basically P wave, S wave, density, porosity, permeability, resistivity, gamma ray, and temperature curves available. The reservoir zone is deep sand directly below Deadwood Formation at 3,380 meters. And the temperature, as we already know, of a reservoir somewhere is greater than 120 degrees by Celsius. Some data conditioning were performed for input seismic data, so this is very crucial to perform quality control of each seismic data we have, of each type of input information we have. So here you can see final angle gathers over this zone of interest, over the geothermal target, with these wells, with this well 1 over this on the top of these gathers. Then, using these wells and with seismic data, pre-stack inversion was performed using that model-based approach in Hampson-Russell. Here is just inversion flow is shown in text. So we have already seen this workflow using using a scheme, as you remember. And here you can see pre-stack inversion result in a form of P impedance section passing through this well 1 and over this geothermal target. As you know, low impedance values in sandstones, shown here in green color, close to green color, are usually good, indicative of good porosity. But this can be confused sometimes with other lithology types like shales. Therefore, independent estimate of VP-VS ratio is very important, and it was done here for this case study. And that's another reason why we need to perform simultaneous inversion, not only acoustic inversion. And here you can see inversion results in a form of VP-VS ratio. Here is map slice of inverted P impedance over geothermal target with wells on the top of that. So we can see some zones with relatively low P impedance. Again, it's shown here using green color. Over where basically we see these low impedance zones over entire map and around the well locations particularly. And here is the same map, but for VPVS property. So as I mentioned previously, independent VPVS estimation is very important. So it's important to note also here what the lowest VPVS ratios are found in the lower part of the survey, near these two wells, near wells 2 and wells 3, but not around this well, not around well 1, where the P impedance values were also low. So now that's why it's important to estimate VPVS as well. So now we have inversion results in the form of these elastic properties, and we will use machine learning to transform these results into porosity and then to permeability. Yeah, so Hampson-Russell emerge was used for that reason. And here on this figure shows training data extracted around well 1, where the target porosity log is shown on the left in red color. And to the right of this porosity log, you can see 5 different attributes which were used to train a neural network. So these attributes are seismic data itself, P impedance, what we obtained after inversion, VPVS, again, which we obtained after inversion, S impedance, and density. And additionally, we have also used some standard attributes like derivative or integrative attributes. They also might be helpful to find the relationship with them. So additionally, we also used nonlinear transforms of all of these input attributes. It's quite a common practice, basically, for all machine learning techniques. When you use any neural network, it's very important not to overtrain it. And to avoid this overtraining, we used this cross-validation technique. Again, it's a quite common practice to use validation for neural networks. And on this figure, you can see training error in black, which uses all the wells, and cross-validation error in red, which leaves wells out, which leaves wells out one by one and perform prediction from the other wells. So note here, but the training error will always be decreasing, as you see here, but the cross-validation error at some point shows its minimum, after which the attributes overpredict the target log. So as you see here, only 5 attributes should be used for this training. And here is a list of these final 5 attributes with also numerical values of error is shown here. So this red box shows these 5 attributes with decreasing cross-validation error. As I said, we have also used nonlinear transforms of input attributes, for example, with square of density volume, which we get after inversion. So in Hampson-Russell image model, we have about 5 different machine learning types. And for this case study, as we had only 3 wells available, we decided to use PNN, probabilistic neural network, as our neural network to be used for this case study. Again, join Pavel, he will expand this topic of neural networks in Hampson-Russell next Thursday. So we used PNN, probabilistic neural network, and here on the left is training error for predicted porosity. Yeah. And black line here, all these black lines here are original logs, and red lines are predicted logs, prediction results. So we had really very high correlation coefficient here, and on the right for PNN training error, and on the right is PNN validation error, and the correlation here is 0.65. So basically, validation error is let's say more realistic way to judge the accuracy of a method than the training error. Using this trained PNN, probabilistic neural network, we applied it to a whole volume and obtained results in the form of porosity volume. Here you can see a section passing again from through well 1 over this geothermal target, and we see at this zone we have a porosity about from 10 to 15%. If we build a map, so here is a porosity map, which is created in a window of 10 milliseconds, picked 42 milliseconds below the Deadwood Formation, so somewhere here at this zone. So the key thing to note here is what this porosity range, if you see on this scale, porosity range is quite small. Here is from 11 to 13%, and we see consistently high porosity throughout the zone of interest, which is very good. Having this predicted porosity, we then attempted to predict permeability, which was for this case study more difficult. Here is log linear cross plot of permeability versus porosity from the Deadwood Formation, where this red line indicates this relationship between permeability and porosity. So using that equation, we obtained a result in the form of permeability volume. And here you can see a section passing through well 1, again the same section. And here is map of predicted permeability created for the same zone as porosity map I showed you before. And as with the porosity map, we see consistently high permeability values throughout the zone of interest. As you can see, an absolute scale has not been used here because we estimated only relative permeability values. So summary for this first case study: a 3D survey in the Western Canadian Sedimentary Basin was utilized for the evaluation of a deep basal clastic geothermal target zone. Seismic pre-stack inversion and machine learning techniques were used to determine reservoir variability and extent to porosity and permeability. The choice of which machine learning technique to use and the parameters selection for this neural network are crucial. And because of limited number of training wells, we found that the probabilistic neural network PNN gave us the best results. So we so far have reviewed the first workflow that GeoSoftware can offer for geothermal projects, which consists of seismic inversion followed by machine learning. But not always, let's say, we able to run with seismic inversion. And in this case, we offer another solution. Another, I would say, innovative workflow, novel approach, rock physics-driven machine learning. And let's now move on to this another case study, another workflow, which could be applied for geothermal projects. So now I will look at this work done by my ex-colleague, Fabien Allo, and his colleagues from Paris, who applied this rock physics-driven machine learning technique to predict reservoir quality in a geothermal reservoir in the Paris Basin, France. This is a carbonate geothermal reservoir. The Dogger Formation is the main hot water and head supplier for approximately 40 low enthalpy geothermal plants currently operating in the Paris Basin. And the success of such geothermal projects relies on the quality of a reservoir, that is temperature, porosity, and permeability. Sources of information from which to infer these key reservoir characteristics, such as wireline logs and cores and 2D seismic lines, were unfortunately scarce. And to address this issue, my colleague John Downton, who is currently working as senior research advisor at GeoSoftware, introduced just in 2020. He introduced this novel hybrid theory guided approach to the generation of seismic data, of synthetic seismic data, which combines the use of rock physics models, statistical simulations. This methodology is applied then by Fabien Allo to generate hundreds of pseudo wells to train deep feed-forward neural networks, DFNNs, for deriving the total porosity, volume and volume of clays in the Dagger formation from recorded 2D full stack seismic lines. And these two properties, I mean the total porosity and volume of clay, subsequently were used to compute the effective porosity, from which an absolute permeability is derived based on laboratory measurements on core data. So it was in 2021, this case study Fabian Law done in 2021, and now in 2023 we have a new technology, let's say, on the top of that, which is realized in Hampson-Russell. Let's now consider this new technology, this new workflow. So as I said, this is rock physics driven machine learning workflow, and we let's say should use this approach when we faced with following challenge, reservoir characterization challenges. And the first of them is limited well control. So when we have only a few wells available, it's very difficult to get reliable results in the interval space, even using seismic inversion. And machine learning could solve this challenge by using pseudo wells for training. So what we can do, we can generate pseudo wells, use them to train neural network, and then apply trained neural network to real data. And using this approach, also other challenges, typical challenges that we faced with can be solved. For example, tin bed detection and complex geology. So that's always challenge, and this approach allows us to obtain high detailed results and deal with fields with complex geology. Of course, the main and the most common, let's say, reservoir characterization method is seismic inversion, and many of inversion algorithms rely on different assumptions, and these assumptions could be simply violated. And machine learning algorithms don't rely on any assumptions, which is also a benefit for us. Again, if we are talking about seismic inversion, many of seismic inversion algorithms using two-step approach for reservoir properties prediction. So as we have seen in previous case study, we inverted for P impedance and then we obtained porosity. So this is some kind basically of error accumulation, and using machine learning we can do direct prediction. We can directly predict reservoir properties. We can directly predict porosity volume, and it's usually not so time consuming as seismic inversion, and allows us to speed up reservoir characterization process due to many of reasons. Here is a graph showing us deep learning benefits from extensive amount of data. And it's quite clear from this graph that the more data we use, the more augmented data we use, the better performance we have. Performance here means the accuracy of prediction. And the question is, if we only have 2 or 3 wells, or even one single well, where we can take this additional data, how we can increase this amount of data and enhance performance of this deep learning. And the answer is generate this data. So yes, proposed solution is generate synthetic catalog consisting of well log and seismic data, synthetic seismic data, based on rock physics modeling and statistical analysis. And then we can use this catalog to train neural network on that synthetic catalog. And that's what you can easily perform using Hampson-Russell GeoAI model. So here is a workflow. Is a workflow of this GeoAI model, of this rock physics-driven machine learning approach. It is basically separated on 2 big stages. So left part here is synthetic catalog generation, and right part is the second stage, let's say, is convolutional neural network applying. Again, my colleague Pavel Didenko will cover this workflow in more details during his talk next Thursday, so don't forget to join him. And now I just would like to very quickly review it. So as usual, as for seismic inversion, and same here, we start with petrophysical analysis. So here we do well preparations, well data preparations, basic conditioning steps, and so on. Required input data are at least one real well, with curves what we need to establish rock physics model, which is suitable for our reservoir. So the list of curves you need fully depend on the rock physics model you use. The next step in the workflow is little layer classification step. So here we break our wells into a series of little layers, and finally we have a little layer, or let's say facies log. Next step is rock physics modeling step. Basically, it's one of the most important steps in this workflow, and the goal of this step is to establish rock physics model, which is linking elastic properties to rock properties, and then we need to calibrate this model on our real data. Next step is statistical analysis. So as you remember, on this little layer classification step, we obtained little layer log, so facies log. And here on this statistical analysis step, we need to establish statistics for each of those little layers. Then all this rock physics model and statistics found on these two previous steps, we use for pseudo well simulations. These simulations can be superimposed to what-if scenarios, applied to some specific layers, in order to generate training examples spanning the full range of expected geology. So here we can specify changes of layer thickness, porosity, water saturation, and so on. And then when we have these elastic curves simulated, we can use them to generate corresponding synthetic seismic gatherers. So this is the, let's say, final step of the first stage in this workflow, the final step of synthetic catalog generation. And now we have large synthetic catalog consisting of pseudo wells and corresponding synthetic seismic gatherers. And on the next step, we will use this synthetic catalog, this synthetic database, to train convolutional neural network on that synthetic catalog and obtain some operator, fully trained on synthetic data. But firstly, let's review, let's back basically to this slide of deep neural networks which we have in Hampson-Russell. So as you remember, as I said, this case study was done in 2021. And for this case study, Fabian Allo generated many pseudo wells and then used them to train emerge deep feed-forward neural network. But now in 2023, we have a new technology, as I said, in Hampson-Russell. On the top of that, it's named GeoAI, convolutional neural network. And input here, input to the CNN, as I mentioned before, are seismic gatherers, and it gives us additional benefits. So we can additionally use synthetic seismic gatherers here, which we generated for each of these of those pseudo wells. So we generated pseudo wells, we generated synthetic seismic gatherers, and now we can use them to train convolutional neural network. And also, again, due to the nature of this algorithm, multiple target properties can be estimated simultaneously. Generally, these CNN convolutional neural networks is used in image classification studies, such as example which is shown here. So here the network is trying to recognize this object on this input picture, and the same basically is happening with our seismic gatherers in our case. So let's now back to this workflow. We stopped at this step of training neural network, convolutional neural network on synthetic database, synthetic catalog. And finally, after this step, we have CNN operator trained on this synthetic data. The next step in the workflow is transfer learning step. So it gives us ability to incorporate real data. So far we didn't use any real data, but now we'll use them in this transfer learning step. And we, let's say, update the operator. So you see it's became bigger, just for a simple explanation. So we updating the operator and, let's say, enhance the results of our predictions. So the goal of this transfer learning step is to address different seismic related effects, like wavelet effects or multiple waves and so on. And generally, transfer learning gives us a lot of other benefits. So Pavel will cover this, all of these benefits in his talk as well. So now, when we have this updated CNN operator, we can apply it to a whole volume. And finally, after this applying, we have volumes of interested target properties as a result. So volumes of P impedance, porosity, what we are looking for, and water saturation, for example. So we know that any property could be used as a target here. It depends on the rock physics model you use for that. Let's now back to this case study. So again, we have already discussed with general slide with general information about this case study. And for this case study, I just want to share with you some of the results. So here is the petrophysical analysis at one of the exploration wells, and you can see they had gamma ray resistivity, neutron porosity, density, and sonic logs as a starting set of logs. And based on these logs, we were able to compute volume fractions of the rock components and porosity using multilinear regression. You can see here, you can see these two curves here, and you can also see the density and p-wave logs on the far right. So they have identified the clays, calcite, dolomite, brine, and oil in this plate. Then they built a rock physics template. So as you remember, this is a very important step in this workflow. They have built this rock physics template based on the cemented sandstone model, superimposed on log data color-coded by gamma ray. And you can see here this red line was obtained with 1% of cement, and it fits the main trend observed in the clean cemented limestones. These two pink lines obtained with no cement delimit marls with an increasing volume of clays. So it is 10% of weak clay for the top line and 70% of weak clay for this bottom line. And here are some of results. So this is here you can see on the top section input seismic data crossing the study area, and the top horizon here, top black horizon, represents the top of dagger formation. The bottom horizon here corresponds to the top of the mouth. And here is estimated total porosity volume, total porosity section of total porosity, showing us porous layers in the upper part of this dagger formation. And it's very well correlates with inserted logs from nearby wells at each of these wells. Here on the top, again, here you can see some results, estimated clay volume and effective porosity. So on the top picture is estimated clay volume, which basically confirmed that the most of the upper part of this dagger formation consists of clean limestones. And on the bottom is effective porosity obtained by combining the estimated total porosity and clay volume, highlighting some layers with high connected porosity. Again, we still have very excellent match at the locations. And finally, here is absolute permeability derived from estimated effective porosity. And you can see here several high permeability layers. Again, they are clearly visible in this upper part of dagger formation, and they represent potential channels for geothermal fluid circulation. Here's some kind of comparison. So on the top is total porosity estimated with using this novel approach, using this rock physics driven machine learning, using deep feed-forward neural network. So it's on the top. And this picture B, is total porosity derived from inverted acoustic impedance using statistical polynomial laws. So these black dotted lines on the both of these sections delimit the highly porous layers in the upper part of dagger formations. So they were able to obtain a much better estimate, much more, let's say, detailed estimate using this deep feed-forward neural network trained on pseudo wells, as you remember. and match at well locations is much better for each of these wells when using that were obtained using seismic inversion and subsequent porosity prediction based on these inversion results. And also this lower layer, if you see here, if you compare this layer here and here, so this layer was resolved very bad basically using seismic inversion, but using DFNN trained on pseudo well logs, we see really excellent results. Also, I need to mention here what input data for this case study was a little bit noisy because of the age of acquiring them. And as far as I know, the idea now is to go back and shoot some newer high resolution 3D seismic to follow up on this technique, on this case study, on this project, on this case study. So some conclusions for the entire presentation. We, as GeoSoftware, has really innovative workflows for energy transition projects. We can utilize seismic inversion and machine learning, applying it to geothermal projects, CO2 storage, or also to wind farm data. I just put here this slide with some papers which has been published on this topic. So if you are interested, you can see them later. I think I will share this presentation, this PDF with you after my talk. Conclusions in this presentation, I discussed how GeoSoftware applications, GeoSoftware tools can be used to map possible geothermal reservoir sites, and there are two recommended workflows: inversion followed by machine learning, and direct using of rock physics-driven machine learning. These are the challenges, again, that we can solve using this rock physics-driven machine learning approach. So it's limited well control, thin bed detection, complex lithology, assumptions. We don't use any assumptions, two-step approach. We use direct reservoir properties prediction, and we can really speed up reservoir characterization. So that's the end of my today's talk. And if you have any questions, please welcome right now. And also you can address them, we can ask them directly to me using this email I put here. Yeah, let me now open chat to see if there are any questions.
Yeah, there is one. Could the real world data used in this presentation be provided?
Could the real data
No.
goes? Yeah.
I mean, Kirill, I'm sure you can answer that, but it's quite unlikely that any example data be provided.
Yeah, I can only provide case studies or even links to these case studies published on different resources. But about the data, no, I'm quite sure that no, we unfortunately cannot provide this data, as these are not open data. Have to check the validity of results. So yeah, both when we use seismic inversion approach or machine learning technique, one of the most common technique is to use blind wells. So we just use blind wells. It's one of the solutions. Just use blind wells, and using this approach, we can see how we can obtain the quality. We can estimate the quality of results what we have. There are also some other techniques which are using for this checking of validation of results. Yeah. So would you say the feature selection CV curve obtained the minimal error? Would you say the feature selection? So what do you mean by CV? Could you please mention, Robert? While you are mentioning, I can ask another questions. What are the minimum number of wells required to produce reliable results using DFNN? So convolutional neural network, with as you understand, this second workflow, second approach I was talking about, it's also deep neural network by convolutional neural network, and for this we need just one well. So we just can generate pseudo wells and train this neural network on these pseudo wells. But if you mean deep feed-forward neural network, which is realized in Hampson-Russell, so from our experience, we can get let's say benefits of using this DFNN. Just for your understanding, using of DFNN is much more time consuming than using of, for example, this PNN, which were used in first case study. And therefore, if you really have benefits of using of this DFNN, you can use it. But for this, from our experience, you need to have at least, I don't know, this is very good question, and the answer is really data dependent. So it's firstly depend on the quality of the well data you have and on the location of these wells from your seismic data. So if you have a good representation of these wells around the seismic area, from our experience, about 7 or 5 wells could be sufficient to get some benefits from that. I have a few questions, if I may, most of the presentations, and one general. Yes, sure. Feel free to ask them.
Predict sonic or P-wave velocity from VSP data using HR.
Is it possible to predict sonic or P-wave velocity from HR is Hampson-Russell. It's possible to predict sonic or P-wave velocity from VSP data. Yes, it is easily possible using Hampson-Russell.
Yeah.
Sorry if I'm misunderstanding this. When you're talking about rock physics-driven machine learning, I'm referring to the synthetic data generation using physics model and not using a physics-informed machine learning approach. Yes, you are right. We use rock physics to generate synthetic data. Yeah, so we use rock physics. We use rock physics for that reason. And you mentioned rock physics. You mentioned a physics-informed machine learning approach. So no, that's not another story. So we use rock physics to generate pseudo logs and then use them to train convolutional neural network on this data set. Yes, it's from some point of view, it's also physics-informed machine learning. So we also give more information, provide more information to neural network to train this network based on this rock physics. Thank you, excellent presentation. Yeah, thank you as well for joining. With regards to this software, how does the software handles imbalanced data sets? Usually the wells penetrate thicker section of non-reservoir than reservoir. So machine learning can have poor prediction performance due to the low number of samples in the reservoir section. Yes, you're absolutely right. And this approach of rock physics guided machine learning allows you to perform. Firstly, it allows you to take some data, for example, from wells which are located on the neighbors neighbors fields close to directed to your fields. So it doesn't matter where your wells is located, where your real well is located. You can use it to model these what if scenarios. And if you know some information, some general information about the geology in your field, you can model these what if scenarios to generate this high number of samples, as you mentioned in your question. So you can use this what if scenarios, you can model what if scenarios and generate samples which as you understand, in your understanding, which are in your understanding cover the full range of expected geology. So, and then when you will train convolutional neural network, this neural network will know these samples, what they are, their presence in your geology.
If I may come back with some petrophysical answers to some of the questions once you are finished. Kirill?
Yeah, sorry.
Yeah, no, I was just saying if I may come back with some petrophysical answers to some of the questions, because some of them do seem to refer to a lot of petrophysics synthetic generation.
Yeah. You're right, yeah. So
Sorry,
basically,
go ahead.
yeah, basically here I see a lot of question. Yeah, how to check the validity of new created synthetic wells? That's basically we don't need to check this validity of these created synthetic wells. We just set some parameters. The thing what we really need to check, what we must check, is the quality of rock physics model what we create on the previous step to generate these synthetic wells. If we trust our rock physics model, we can trust our synthetic wells which we creating using this rock physics model. Yeah, many questions from one person. So in simultaneous inversion, what's the basis of choosing the order in which the sequential simulation is executed? I mean, simultaneous density when co-simulating VP, when co-simulating VS. So in simultaneous inversion, it comes from its name, simultaneous inversion. All these properties are simulated, are predicted, are inverted simultaneously. So the thing what we need to do is to perform a feasibility analysis using well data. So we need to build a crossplot. Crossplots, I mean, P impedance versus S impedance crossplot, VPVS versus P impedance crossplot, P wave versus S wave crossplots, and see using which crossplot we can better separate our target reservoirs, our target zones. And based on that, the only thing what we can do, we can select it calls parameterization of this simultaneous inversion. It might be P impedance, S impedance, and density parameterization. So in case of using of this P impedance, S impedance, density parameterization, we will have inversion results in form of these free elastic properties and so on. And all these elastic properties were inverted simultaneously. Yeah, in the first example, Y is the target square of porosity. Let's check, but it shouldn't be square of porosity. The target should be just porosity. So in the first example, yeah, let's me back to that slide with, yeah, this is the first case study, and you see this target curve. It's not square of porosity, it's just simply porosity. If you mean, yeah, here, yeah, finally for this immerse training, as I said, we used in this case study, and this is really very common practice, to use nonlinear transforms to attributes. We use these nonlinear transforms both for target property, in this case is porosity, and for attributes which we used to find the relationship with them. So for training, for neural network training, yes, in this case, you're right, we used square of porosity, but then the final results what we have after prediction, it's of course not the square of porosity, it's just the porosity as it is. Yeah. Yeah, next question. Where did the permeability values come from in the porosity permeability relationship? So permeability values come from core analysis, well data core analysis from the laboratory measurements. It comes from well data. How we can get volume of shale and volume of clay from petrophysics before using it in rock physics of inversion. Yeah, it's again mostly question for regarding petrophysical process, but typically, yeah, it's better to refer. Let me answer for you on that question using email. So if you write me your questions, I think you have you even have more questions, I can answer on them. Just they're relating to petrophysical aspects, and it's better to discuss it with my colleagues with petrophysics, and I will get you. I will provide you with accurate answer. Next question. When upscaling fine grit from inversion to fluid flow reservoir models, for example, if my inversion grid resolution is 12.5 meters by 12.5 meters and 2 milliseconds, how to decide on the upscaling for fluid flow modeling? That's a good question. So basically, to get accurate models for fluid flow modeling, it's always better to get these models directly on the fine grid. So in this case, we provide this workflow in JSON. So JSON geostatistical inversion gives you ability to get these results on this fine grid and use it directly for rock physics model. Yeah, thank you for joining as well. So reach me out using my email. I don't know if people see all questions in chat as well as me, but I think yes. Could you confirm, please?
Yeah, I think we have covered all the questions. Now, from the petrophysics point of view, couple of things I'll point out. Number one, for the generation of the properties, it is the usual petrophysical interpretation that you can use to get the values of V shale, porosity, phi T, phi E. Core data can come in to provide permeability. You can set up correlation between porosity and permeability, and that should give you other necessary data. With regards to generation of synthetic data, you have to establish which is your data that is unaffected by the data acquisition process. And once you have established that, then it is quite important to know which section of the reservoir thickness, or rather subsurface thickness, you want to generate the synthetics for. And once that is established between the geophysicist and the petrophysicist, then it is possible to generate the synthetic data from the available data. As part of the PowerLog software, there is a inbuilt confidence level indicator when you're generating the synthetic data to indicate what level of confidence the software is currently predicting to have in the newly generated data that you have. So that becomes a very handy tool as per the petrophysics for the petrophysicist rather, and that allows you to first of all gauge whether whatever you're predicting is good or not. Secondly, once you have predicted the data, there are simple petrophysical principles that you can follow, fundamentals of petrophysics you can follow to check whether the data generated is sound or not. Because end of the day, you know the rock type, and petrophysics will behave in a particular way for a particular rock type, considering the subsurface conditions and the compaction levels in the subsurface. So all these information becomes extremely handy when you are working with the logs, and you have to use your petrophysical mind to get these answers. I hope that does answer some of the questions that you may have from the petrophysics point of view.
Yeah, thank you, Kanat, for your contribution. And also, yeah, there was a question from Haifa. Sorry if I pronounce it's wrong. So yeah, I didn't answer it on your question directly, but as I said, it depends on the parameterization you use. So you perform feasibility study, and if you see separation of your target reservoir in VPVS versus in VP versus VS cross plot, of course you can invert directly for VP and VS, and it will be useful for you. Yeah, and also information for all of you. Pavel Didenko, my colleague, I was mentioned him several times. He will have his talk next week, next Thursday. He is in the chat as PD, so it's he, and you can trust his answers. Yeah, he has answered some questions as well. So I think we answered all questions that we have in chat. If someone has more questions, please welcome or ask it directly using my email. When you divide P impedance with density, you will get velocity, right? Yes, of course. Yeah, we also, if we use, for example, P impedance, P impedance, S impedance, and density parameterization for inversion. After this, when we have these volumes, we can simply calculate any derivatives based on all these volumes. And also our software has a capability to directly, when we do, for example, inversion in Hampson-Russell, we can have results simultaneously for P impedance, S impedance, density, P wave, and S wave, and also for residuals. So yeah.
All these values that you're generating and calculating, you can plot cross plots in the PowerLog software, which becomes very handy to check whether your data is actually in range or not. And because many a times the subsurface well attributes contribute to the erroneous data when you're when you are dealing with the logs. So that becomes a very handy tool to judge whether your interpretations are correct or not, and whether the data seems to be within the range or not, essentially.
Yeah.
Well, thanks a lot, Kirill. Looks like we have run out of questions. So thank you very much for your presentation.
Yeah, just a quick question. Do you need my presentation? Do you want to share it with all attendants or not?
Yeah, please do share it with Javad, and we'll share appropriately with everyone.
Yeah, thank you.
And of course, any sensitive data, feel free to sensitize that, and then feel free to share it.
Yeah, thanks. I will.
Yeah. Okay, thanks everyone for attending, and I hope you have a wonderful weekend wherever you are.
Yeah, thank you all.
Thanks.
It was a pleasure to give this talk. Bye-bye.
Thanks, Dave. Bye. Thanks, Pasha.
Thank you. Bye-bye.